Cool. Okay. LakYah, thank you so much for joining us today. I'm super excited about your talk. LakYah is also a student with me at Northeastern, as is John and Sean, so a decent portion of this quorum. But we study completely different things, so this is like all pretty new material for me and probably for most of you, I'd imagine, as well. So I think that'll be a lot of fun. And I'm just going to go ahead and immediately give the stage to LakYah. You may be interrupted by dings as a couple more people join over the next couple minutes, but they can figure things out if that happens.
No problem. Okay, so hello everyone. My name is LakYah. Today I'm presenting on nearly
I'm so sorry. I massively butchered your name.
It's okay. No worries. Yeah, so today I'm presenting on nearly optimal property preserving hashing. This is a work that was featured at Crypto 22 or Crypto this past year. And it's joint work with Justin Holmgren from NTT, Minghao Liu, and Daniel Wichs, who is my advisor. Okay. All right, so I'm going to start by giving you guys a little bit of background on property preserving hashing and go into a little bit of motivation. And then I'm going to go into some coding theory basics that will kind of like help to understand our constructions, and then move on into our constructions and talk a little bit about bounds, and then end with some open questions. Okay, so what is a property preserving hash? We have this hash function h, which takes as input an n-bit string x, and then outputs an n-bit string h of x. Okay, and so we can consider this binary property p of xy that is equal to 0 if the property does not hold and 1 if the property does hold. And we want that if we're given h of x and h of y, we're able to determine if p of xy holds. Okay, so a little bit more formally, a property preserving hash family for some binary predicate p consists of this family of hash functions, curly h, and the following algorithms. And also feel free to like stop me at any point and ask questions if something is not clear. Okay, so we have our SAMP algorithm, which samples one hash function from that hash family. And then we have our eval algorithm, which takes as input a description of that hash function, and then h of x and h of y, and then outputs 0 or 1.
Sorry, so I have a question.
Yes.
So when you talk about property preserving hash, for me, I don't know anything about this stuff. It feels like for me it's that some property is preserved before hashing and after hashing. So some property it's true before hashing. Some property is true after hashing if it's true before hashing. But in here you are using a binary property. Is there a particular that doesn't seem so the property I described seems like a unary property instead of a binary one.
No,
so is there a particular reason that you use a binary property?
Yeah, so it just depends on the property that you're like interested in preserving. You can have unary properties, but binary properties most commonly like preserve relationships between two objects. So like if a relationship holds between let's say x and y, we want that same relationship to hold, you know, with all but negligible probability after we hash those two objects.
Okay, I see. Makes sense.
Okay. Great question. Okay, so we also have to satisfy these additional properties. The first is correctness, which states that for every xy, the probability that our eval algorithm outputs something different than p of xy is negligible. Okay, and so we also define this additional property called robustness, which means that for every PPT adversary A or PPT algorithm A, correctness still holds even when this algorithm A has seen a description of our hash function and is able to choose x and y a priori. Okay. Sorry. Okay, and so to better understand the difference between non-robust property preserving hashing and robust property preserving hashing, we can look more closely at the difference between universal hashing and collision resistant hashing. especially when it pertains to the equality predicate. So the equality predicate just takes two, it's another binary predicate or binary property, which takes two objects and determines whether or not they're equal, as the name suggests. So a universal hash is exactly a non-robust property preserving hash for the equality predicate because it satisfies this first correctness property. Okay. And a collision resistant hash is a robust property preserving hash for the equality predicate because we have this additional it satisfies this additional robustness property.
Sorry, I don't mean to interrupt, but for the negligence, like what order is that on, like O of epsilon, for like if you're comparing it to like a traditional proof? Like what makes it, like what order makes it negligible?
So it's like so negligible means like on the order of like one over two to the like lambda, or like lambda.
Okay, so okay,
Yeah.
right, okay. So that's how you like preserve your metric. Okay.
Yeah. Okay, so in the last slide, we talked a little bit about the equality predicate, but let's say we wanted to compare objects based on some other property of similarity that we define arbitrarily. So Apple attempted to do this with their neural hash algorithm. They wanted to be able to compare the hashes of images that were known to contain child sexual abuse material, or CSAM, with the hashes of the images that were stored on their cloud, and kind of like determine if there was some similarity between those images. Unfortunately, their solution was not robust because an outside party or outside parties were able to find two completely different images that hash to very similar outputs. And this is, of course, very problematic. And in this case, the question would be, how can we actually present or create more robust solutions to this issue? And our suggestion is that through development of more robust property preserving hashing. Okay, and facial recognition is kind of like a very similar issue. We're just trying to determine if two different images are of the same person.
By the way, my brother's face can unlock my iPhone.
Exactly.
So,
Exactly.
facial recognition is also not that amazing.
Yeah.
He's 15.
Yeah, so in this work, we focus specifically on the Hamming property. And it just determines if the distance between two strings, x1 and x2, is less than some threshold t, or less than or equal to some threshold t, or greater than that threshold. Okay, and then we also mention the gap Hamming predicate, which determines if the distance between those two strings is less than or equal to this threshold t, or greater than or equal to 1 plus delta times t. And in this little area, this little gap area in between, we don't really care about what the output is. So it's a little less well-defined than the exact Hamming predicate or property. So why did we decide to study Hamming? Hamming serves as a very basic unit of measure and can lead to us understanding even more complex metrics like this, like the metrics that were used to kind of build this neural hash application. Okay, and it's also used as a common method of like measuring the similarity between feature vectors and machine learning. So this is like good evidence that we're like moving in the right direction when we're deciding to study Hamming. Okay, so the first work in this line was by Boyle, Levine, and Vaikuntanathan in 2019. And they presented two constructions for the gap Hamming predicate that I described in the last slide. The first was based on standard collision resistance, and it achieved a fairly decent output size. Okay, and then the second one was based on this new assumption called the sparse SIS assumption that was introduced in the same paper. So it's a little less standard than collision resistance, but it did enable them to get a better output size, or a smaller output size, which is what we're trying to do. Okay, and the next work after this introduced the first example, or the first construction for exact Hamming property preserving hash for Hamming. Yeah, sorry, exact Hamming property preserving hash. And this construction was based on another, similar to the last construction, was based on an assumption that was introduced in this work as well. So it's very non-standard, but it also enabled lib to get like a fairly decent output size.
Okay, you have a question in the chat from Kai. He's wondering, is sparse SIS a relevant concept to know here, since I think probably most of us don't know what that is.
No, it's not. I'm sorry. Yeah, no,
No,
it's not particularly. I'm just mentioning this to compare to like the assumptions that we use in this particular paper.
Sure.
Okay. And then, yeah, so the only important thing to note about sparse SIS is that it's not standard. Yeah. So the next work was by Fleshhacker, Larson, and Simpkin, and it's the second exact hamming PPH that we have. And this is based on a more standard assumption. So while sparse SIS is not standard, like regular SIS is a little more standard. And it's definitely more standard than this Q-strong bilinear discrete log assumption. And they were able to achieve the same output size. So our question, or the obvious question to ask from these prior works is, can we achieve a robust property preserving hash for hamming, specifically for the exact hamming predicate with more standard assumptions, and achieves like a very good output size. So this O of T log, or this O of T lambda, it's decent, but we believe that we could do a little better. And so that's what we're trying to accomplish in this work.
To be clear, these assumptions are like, you're assuming that some problem is hard, right? And then I guess like a bad assumption is one where the problem is super esoteric and nobody knows anything about it. And a good one is where it's like a reasonably well understood problem. Is that right?
Exactly. Yeah.
Okay, cool.
Okay, in this work, we present two exact hamming PPHs for we produce two exact hamming PPHs. And the first is based on SIS, or discrete log, and we show that we're actually able to get an output size of less than T log n. And then we prove a lower bound in the same paper that shows that this actual output size is optimal. So it's pretty much the best that we can do. And so it's a great achievement. And then our second construction is based on standard collision resistance, which is the more ideal assumption to, or I guess the more, I would say, the more ideal assumption to base constructions on compared to the SIS, or discrete log. And we were able to achieve that, or to achieve a similar output size as the prior works. Okay. So again, for the remainder of this talk, I'll go over some coding theory basics and then move on into our constructions. Okay, so the first thing from coding theory that we will need is this NKQ, error correcting code, which is defined by this matrix G. So if you multiply this matrix G by some message M, we get what's called a code word, and we label that with C. So in the event that we want to transmit this code word, and let's say some error occurs while we're trying to transmit the code word, this error correcting code will allow us to recover, up to a certain extent, recover from any error that has occurred during transmission. Okay, and in order to do that, we need this parity check matrix, which has a very special property that P, or this parity check matrix P times any code word, is equal to 0. Okay, and so the process, or a process for actually recovering from error that occurred during transmission, is known as syndrome decoding. So let X equals a code word C plus some error vector E. Given the syndrome S equals P times X, we are able to recover an error such that the Hamming weight of that error vector is less than or equal to T. Okay, and so it's not immediately apparent how we can recover this error vector E just based solely on this syndrome P times X. But if we do a little bit of substitution, then we can see that our syndrome is actually reliant only on our error vector, or only on our parity check matrix P times our error vector. And so this fact or this relationship is what actually allows us to recover that error vector. Okay, and so syndrome list decoding is a very similar process to syndrome decoding, but instead of recovering a unique vector E, we recover a list of possible error vectors such that the size of that list is polynomial in N. Okay, and we define the rate of a code word to be a ratio between the size of our message M, or sorry, the size of our original message, which is of size K, and the size of our code word, which is of size N. So the code word is gonna have to be a little bit longer than the size of the original message because we need to allow additional bits to enable error correcting. We need a little bit more information so that we can actually recover that error. But ideally, we want this to be as close to 1 as possible. We want to be able to add the least amount of extra bits that we can. In an ideal world, that this will be possible, but there's this impossibility result known as the Hamming bound that tells us that it tells us we can't get to 1, but the closest we can get to 1 is R equals 1 minus H of T over N, where this H of T over N is binary entropy. Okay, and then unfortunately, currently we only have inefficient codes that meet this Hamming bound. If we want to meet, if we want to have efficient codes, which is, ideally what you would want, we are able to meet this lesser or slightly weaker bound known as the Bloch-Zyblov bound, which tells us that our rate can be equal to 1 minus this HBZ term, where this HBZ term is slightly larger than binary entropy.
Is that like a theorem that if you want efficiency, then you have this bound, or is it just like empirically true that nobody's figured out yet how to break past that bound while being efficient?
Both.
Oh, okay.
Yeah. Hopefully the coding theorists will, I don't know, we'll come up with some very good codes that will meet the Hamming bound sometime soon, but as of now, we can only do that inefficiently. All right, so our first construction is a non-robust property preserving hash, and it utilizes syndrome decoding and universal hashing, which I will explain in the next few slides. But first, let's again briefly remind ourselves of the Hamming property. Let D of x1, x2 be equal to the Hamming weight of x1, XOR x2. Okay, and then Hamming is equal to 1 if that distance is less than or equal to t, and then 0 otherwise. A universal hash for some input x and some matrix A is defined as h of x equals a times x. Okay, and so this hash function satisfies this universal property, which states that for every x1, x2, such that x1 is not equal to x2, the probability over the randomness of that matrix A that the hashes of those two strings are equal is negligible. So this 2 to the minus m is a negligible fraction of m. Okay, and so this also satisfies this homomorphic property, which states that for every x1, x2, a times x1 minus a times x2 is equal to a times quantity x1 minus x2. And so those are the two properties that we require in any candidate hash function that we will be able to utilize for our constructions. All right, so a little bit more formally, a R2P2H or a property preserving hash for Hamming. We let P be the parity check matrix of an NK2 error correcting code. Using that sample algorithm that I described earlier, we sample our hash function H and define H of X to be P times X and A times X. Okay, so let H of X1 be defined as PX1 and AX1 And then h of x2 we define similarly. We compute the difference between px1 and px2. And then we perform syndrome decoding to again retrieve this list of possible error vectors, such that for every EI in that list, P times EI is equal to P times X1 minus P times X2. And additionally, the Hamming weight of each of those EI vectors is less than or equal to T. Okay, and so if there exists an I in that list such that, or an EI in that list such that A times EI is equal to A times quantity X1 minus X2, then we can output 1. Otherwise, we output 0. And so the idea behind this particular construction or this particular evaluation method is we're treating the difference between this syndrome here, this PX1 syndrome, and this PX2 syndrome as the error that we're trying to recover. Or sorry, we're treating the difference between this X1 and X2 vector as the error that we're trying to cover using the difference between their two syndromes. Okay, and then we can show that security holds because if X1 and X2 are indeed close, then that means for sure we will find an EI in that list such that this relationship here holds. On the other hand, if X1 and X2 are far, meaning if the distance between them is greater than T, then it should be the case that for every possible error vector in this list, A times EI is not equal to A times X1 minus A times X2. Right, does that make sense? Cool.
So just to clarify, the purpose of finding such error is to eliminate them, right? We don't want such errors.
So the purpose, so we're trying to determine if the distance between X1 and X2 is less than this threshold T.
Mm-hmm.
So if we can recover an error vector who has a Hamming weight that's less than T, such that this relationship holds, then we can safely conclude that the distance between X1 and X2 is less than T, or less than or equal to T.
Okay. Normally we would want our distances to be greater than T, right? So that codes do not overlap, like we have distinct codes for distinct vectors.
Right. So, okay. So yeah, you're correct. So in this case, we're using, I guess it's like we're trying to address a different problem. So the code word, or the minimum distance between code words, is what we're calling T here.
Right.
And so if we can recover an error, so okay, so during this syndrome decoding process, we're going to always recover an error vector that has a Hamming weight that's like less than or equal to
T.
That's less than or equal to T. So we can't, since we can only recover up to T errors based on the based on this code, then for sure all of these will have a Hamming weight less than or equal to T. But it's not the case that just because the Hamming weight of the error vector is less than T, that we can conclude that we can conclude that the distance between X1 and X2 is also less than T. And so we have to perform this additional check to verify if that is in fact the case.
Okay. Cool. Thanks.
Yeah. Did that answer your question?
Yeah. I was not clear about what role T has. Okay, got it.
Yeah, so T is just our threshold for this particular property that we're trying to, so we're trying to make distinctions between the case where X1 minus X2 is less than that threshold. So yeah, the whole point of this like construction is to like differentiate between the two cases of where the first case is where the X1 minus X2 is less than that threshold. And the second case is if X1 and X2 is greater than that threshold. So we have these two cases, and then we're using this particular method of evaluation to determine which of those two cases that we're in.
Okay. Got
And
it.
so T is kind of like the line in the sand that tells us in which case we're in.
Got it. Thank you.
Okay, so in our paper, we define or we write a few corollaries that give upper bounds for our output size, which is of the form m is equal to n minus k plus lambda. And we do this using an NK2 error correcting code, which can list the code up to T errors. Again, as I mentioned earlier, we only have inefficient codes that meet our Hamming bound. And using those codes, we can get an output size of m equals h of t over n times n plus lambda. And then again, if we're using efficient codes that match that block-Zyblock bound, then we get a slightly larger output size, but it's very close. The difference between these two, between this HBZ term and this H term is not very, very large. Okay, and additionally, if we're using this HBZ, if we're using codes that meet this HBZ bound, then we can always get a non-trivial compression for up to a constant distance T, which is equal to O of n. And then we can also always upper bound, regardless of what T is. We can always upper bound the size of the output by m equals O of T log n plus lambda. But in the case where T is large, we can do a little bit better because this log in term disappears as this T term gets very large. Okay, so our first robust PPH is from discrete log or SIS, and we will also be utilizing syndrome decoding for this one as well. So let's first kind of describe the difference between this construction and our last construction. So these constructions are very similar. They only have one or two very major differences. The first is that instead of using a universal hash that I explained previously, we're going to be using a homomorphic collision resistant hash. And I'll also define what this is. And our constructions that we have currently for homomorphic collision resistant hash functions are based on discrete log, and we get that from Pedersen. And then the second one is from SIS, which we get from ITI. And this achieves essentially the same parameters as our first construction, even with these differences that I'm describing here. Okay. I'm actually not don't have time to get into, I don't have time to get into the difference between, the specific constructions for collision resistant hash functions. But we do include those in our paper if you would like to take a look. So I'll get into our second robust property preserving hash, which is based solely on standard collision resistance. And we're kind of utilizing the construction from one of the prior works, which is for gap hamming. And we're using that gap hamming construction along with syndrome decoding to produce an exact hamming construction. Okay, so let's remind ourselves what the gap hamming predicate says. Let D of x1, x2, again, equal the hamming weight of x1, XOR x2. And then gap hamming is equal to 1 if that distance is less than or equal to T. It's equal to 0 if that distance is greater than or equal to 1 plus delta times T. And then it's equal to about otherwise. More formally, for our robust property preserving hash, let H gap be the robust property preserving hash for gap hamming. And then similarly to before, let P be a parity check matrix of an NK2 code that can efficiently list a code up to, can efficiently decode up to 1 plus delta times T errors. Similarly to before, again, we sample our hash function H, and then define H of X to be P times X, and then H gap of X. So we're utilizing this hgap hash function from the prior works as a black box. And then we're just essentially just concatenating that onto the syngem p times x. For evaluation, let y1 be equal to px1 and then hgap of x1, and then y2 be defined similarly. Again, we're going to compute the difference between px1 and px2 and perform syngem decoding. And this time we get a unique error vector E such that P times E is equal to P times X1 XOR P times X2. And then again, the Hamming weight of this error vector E is now less than or equal to 1 plus delta times T. All right, so we output 1 if and only if this eval gap, which is the evaluation function from the prior works. Again, we're using this in a black box way as well. So we just compute this eval gap function, or compute this eval gap and check if it's equal to 1. And then additionally, we check that the Hamming weight of that error vector E is less than or equal to T. And if these two things are true, we can output 1. And we can conclude that the distance between x1 and x2 is in fact less than or equal to T. Okay, lastly, we have this additional construction for a randomized robust property preserving hash. The difference between this construction or these this like class of robust property preserving hash and the last is with our first three constructions, or sorry, our first two, our second two constructions, so construction 2 and construction 3, for robustness, we needed at least collision resistance. But with this randomized version, we can get robustness information theoretically. So we don't need any computational assumptions at all for robustness. So for an overview, h of x is computed using a randomized process. And then our adversary can choose worst case x and y after seeing a description of our hash function, and then is able to win or succeed if it's able to find an xy such that eval outputs something different than p of xy. Okay, so our R2P2 hash for Hamming, or our randomized robust property preserving hash for Hamming, we have this construction from prior work, which is an information theoretic randomized robust property preserving hash for the equality predicate. And that's able to produce an output size of O of square root n. And in this work, using that construction or using techniques that are used in this prior work construction, we produced an information theoretic randomized robust property preserving hash for Hamming. Okay, and then we achieve an output size of O of square root lambda n plus f of tn, where this f of tn is equal to this binary entropy function times n. And of course, this is less than less than t log n. Okay, so in our first three constructions, we noticed that we are able to use syngem decoding plus a homomorphic universal hash function for equality to produce, or in R2P2H, an R2P2H for equality to produce an R2P2H for Hamming. So similarly, in this randomized setting, we're going to use syngem decoding along with a homomorphic randomized robust property preserving hash for equality to produce a randomized robust property preserving hash for Hamming. And again, this second part is where we get, or is what we get from prior works. To summarize our results, we produce 1 non-robust property preserving hash for Hamming and 2 robust property preserving hashes for Hamming. Our constructions are conceptually simpler than the prior works, and we're able to achieve better compression under minimal assumptions. And then we also introduced this new notion of randomized robust property preserving hash for Hamming, or specifically for the Hamming property. And in our work, we present an information theoretic construction that also achieves optimal parameters or an optimal output size. Okay, and so the open question that I would like to leave you guys with is, in our work, we define a lower bound for our constructions in the robust setting for exact Hamming and gap Hamming for our output size, and we say that we can achieve an output size of m equals this binary entropy function minus little o of 1 times n plus lambda. So this is a lower bound for both gap and exact Hamming. Essentially, this matches the non-robust exact parameters. So we have robust gap, robust exact, and then we have non-robust exact. And they all say, or sorry, and our lower bounds say that they all can achieve a lower bound, or sorry, the minimum size for the output size that they can all achieve is this expression right here. There is a prior work that says that in the non-robust gap setting, we can achieve an even smaller output size that is equal to O of lambda. Currently, we don't have any, there's no knowledge of whether or not we can meet this smaller output size in the robust gap setting. And so we're kind of trying to figure out if there are constructions that we can produce that will actually get us to this lower output size for our robust gap setting. And that's it.
Okay, thank you so much.
Take any more questions.
That was fantastic. I think I'll open up with a question, and then other people may have questions as well. I was a little confused about the universal hash functions being linear. Like, I thought the hash functions were by definition supposed to be nonlinear, but when you define a universal hash function, it's a matrix, right? So that's a linear transformation. Isn't that kind of insecure because you could figure out what the matrix is and then you can like undo the hash, or is it just am I missing something?
So we're not particularly okay. So the properties that the properties that we're focused on is or I guess the things that we're focused on is like preserving the properties and not necessarily like secrecy. So I think that's what you're asking. Yeah. So secrecy is kind of like I guess it's like a byproduct of like if you're only seeing the output of the if you're only seeing the output of the hash function, then I'm not sure if you can directly, like, even if you know even if you know that matrix A, I'm not sure if you can like directly very easily figure out what X is. Okay. Yeah, but I think that's like a byproduct of us using this this particular hash function. It's not necessarily something that we're trying to guarantee.
I see. Okay. So what's like a use case? Would homomorphic computation be an example of why you would use hash functions like this? Like what sort of systems are you building where you want these properties?
So yeah, like the example for neural hash. So they were trying to, so the property that so I don't know particularly like what exact metrics they were using to like perform these evaluations, but ideally they would have come up with some, I don't know, some metric to distinguish images that contain, CSAM from images that like does not contain CSAM, and they wanted, after hashing, those properties would still be, you would still be able to determine what those properties were.
I see. Okay.
If that makes sense. So that answers your question.
Yeah, absolutely. If other people have questions, they should just unmute and ask away.
Yeah, I got one. So first of all, that was a really great talk. That sounds like some really cool work that you're doing. So congratulations on getting into crypto. That's awesome.
Thank you.
So I have a question, sort of more along the like application side of things, where there's sort of like two. I'm not sure familiar you are with like image hashing in general. So stop me if I'm like telling you stuff that you already know.
Okay.
But the sort of like tool schools of thought right now are going through and enumerating like known types of images and sort of just creating those as exemplars. And then you want to build some sort of like constant time hash function that will go through and spit out a digest that is robust to some things, right? So like translations, flipping, maybe stretching it, shrinking it. And then there's one where you go through and feed it through a giant neural network, and then you lop off the last layer or something along those lines, and you're left with a vector. And you can construct these models in a way where these vectors, where the images have some sort of semantic similarity, where that's sort of never really rigorously defined, but it's images that are similar in some way, where in the like embedding space they're close by, which happen to oftentimes look similar, where the higher the cosine similarity, the closer the images are to being near duplicates, maybe with a couple of pixels changed. So what I'm curious is there a way to take your construction and apply it to something like locality sensitive hashing, where you want to go through and have a property that is based on the like inner product between the resulting vectors here? And you can even go through and like quantize the vectors if you need, right? Because I think your construction was for discrete stuff, but you can always, quantize floating points. But yeah, so I think that's my question. Like, is it possible to like take this construction and effectively construct the property that like, yeah, like I would like this property to be if the inner product of these two vectors is this, sort of the cosine similarity is bounded by that, and sort of like pull it into like the continuous space?
I don't know if there's a way to directly use our constructions to do that. I think maybe so the way that the constructions for preserving like properties or different properties often like vary. This line of work isn't very long, but the constructions for different properties kind of like vary a little bit. So they're not like, it's not like a direct correlation between mechanisms that will allow you to preserve like Hamming distance versus mechanisms that will like allow you to preserve other properties. So even if there's like some like slight variation between the properties that you're trying to preserve, I'm not sure like how great an impact that would or how large an impact that would like that would have on your ability to like still maintain robustness.
Got you.
But certainly there if there's like a need to like preserve these properties and the properties are like well defined, then we can come up with additional constructions for those.
Cool. Thank you.
Okay. Did that answer your question?
Yeah, I think so. I think I also have to go and read your paper after this.
Okay. Thank you.
Cool. Well, if there's no more questions, we may call it a day. But LakYah, thank you so much for talking to us. Again, I'm sorry I completely butchered your name, but
no, it's okay.
Now I know how to say it correctly. This was a lot of fun and super interesting. Regarding the video, do you prefer that I just like put it in the Slack so that people who want to see it can watch after the fact, or do you want it like up on YouTube? We put some talks on YouTube if people want it up, but if not, it doesn't really matter. What's your preference?
I don't have any. Whatever.
Okay.
Whatever is.
I'll put it on YouTube if you don't mind, because sometimes we're surprised. Like we had a talk that literally 4 people came to and over 100 people watched on YouTube. So nice. You never really know. But excellent. Thank you so much for talking to us. This was really fun and a nice way to end a Sunday. So yeah, thank you for your time.
Saturday.
Yeah, thank you, LakYah.
Is it Saturday?
No problem.
Yeah, it's Saturday.
Saturday.
Oh yeah. Cool.
Must have been a rough week.
Yeah. All right. Talk to you later.
Great.
Bye.
Bye.